Welcome everyone. My name is Troy Hunt and today I wanted to talk to you about how your website is being pwned while you're not looking. I'm an MVP for developer security. Such a thing does exist. I didn't know it existed until last year, but apparently it does. So my focus is on security in applications and predominantly ASP.NET applications. I'm the author of the OWASP Top 10 for .NET Developers series. There's a free ebook on my website, so one of the things I'm going to encourage people to do, go to troyhunt.com, grab that book, it's free, it's got everything you want to know about security for ASP.NET as related to the OWASP Top 10. And I'm also the creator of a website called A Safer Web, which looks at security vulnerabilities in websites, mostly due to misconfiguration. So you can go to asaferweb.com, put your domain in, it will come back and tell you hopefully everything's good, or a few things might be bad. So what I wanted to talk to you about today is website security, and I'm going to talk a little bit about this website pwning. And I've seen this term used a lot, and I wasn't exactly sure what is pwned. You know, all these websites keep getting pwned. So I went to the source of all knowledge, which is Google Images, and apparently pwned is getting your head eaten by a massive white whale, which didn't seem to sort of fit the context. So I went a little bit further, and they said, well, pwned is when you get hit by a snowball thrown by none. Okay, but you know, we're not quite getting there. So the next source of all truth, Urban Dictionary on the web. And what the Urban Dictionary tells us is that pwned is a spelling mistake. It's owned, pwned, OP, O key and the P key, too close together. But in the context of today, pwned is really about being owned or dominated by some godlike or computer force. So we're really going to talk about websites getting hacked and what we can do to protect them. So where I thought we'd start is just a quick look at who is getting pwned. And the bad news is that just about everybody is getting pwned at the moment. Every time I prepare this slide, I've got more and more and more icons I've got to add. And even just before this one, I had to, okay, now I've got to add in LinkedIn, I've got to add in Last.fm. I ran out of room for eHarmony. But we've got a pretty broad range of companies on here. We've got shoe companies, two-factor authentication companies, military contractors, they make freaking jets, Lockheed Martin, Pwned.com, probably not the kind of place you want your details leaked out of, if anyone has details there. So everybody is getting pwned in one way or another. I did want to put a bit of context to this as well though, because this tends to sort of be this faceless pwning that goes on the internet. And the reality of it is that this pwning is sort of breaking down into three different categories of people that are hacking our websites. And the first category is online criminals. And these guys want to make money. They obfuscate their identity by wearing ski masks and gloves. They are people like this guy, Stephen Watt. So he hacked about $200 million worth of credit cards out of TJX, a big department store in the US. Uses these credit cards to then fund a very lavish sort of lifestyle. Alfred Gonzalez, tied up in the same sort of deal, relaxing back in a penthouse suite, paying for the rooms with the credit cards that he has stolen from other people. Or Dmitry Golubov from the Ukraine, installing Trojans on people's machines, stealing credit cards. Then a similar sort of deal. They'll either use those credit cards to go and buy things themselves, and they've got all sorts of ways of then getting products delivered without being traced back, or they'll sell them on the black market. There is an internet black market for selling credit cards and bank accounts. So the next category everybody's probably very familiar with is the hacktivists. So that's people like lulzsec. So lulzsec had popped up in all sorts of different places. They were the guys that hacked Pwned.com, 26,000 email accounts out of Pwned.com. Anonymous, everybody knows about Anonymous, everybody's read about Anonymous. They've got a whole list of things behind them. They've got a whole list of things that people saying that they were anonymous did, but they're anonymous, so we don't really know whether they're anonymous or not. What we do know is that they've done things like hacked Stratfor. So security intelligence or security briefings is what Stratfor did. Late last year, they were hacked, and there were a whole bunch of bank account details and credit card details that were extracted from Stratfor, which Anonymous then used to go and make charitable donations with, which probably didn't end up very well because most people probably cancelled the credit card and then the charities had to go through all the rigmarole that comes as a result of that. And more recently, groups like UgNazi, and UgNazi hacked WHMCS, the payment gateway, about 6 weeks ago. Grabbed about 500,000 usernames, passwords, and some credit cards out of there. So all of these guys are sort of these loosely knit groups who try and, I guess, collate under one banner. Motivations are, they say, for a greater cause. Sometimes I think it's probably infamy. Sometimes it's probably that they're a little bit lonely. And we'll look at some of those guys a little bit later on. Now the third one, and this is where it's starting to get really interesting, is around these nation states. So this is governments. This is governments engaging in the term that's being coined now as cyber warfare or cyber espionage. So they're the ones who are creating things like Stuxnet. So Stuxnet, taking nuclear facilities, not so much offline, but disabling capabilities of nuclear facilities in Iran, slowing down centrifuges and propagating by USB sticks across airlocked networks. So that's serious intelligence that goes into there. Things like DUKUs, so targeted industrial control systems, SCADA systems from Siemens. Again, runs everything from nuclear power plants to water treatment facilities. Serious stuff. And then very recently, Flame as well. So Flame appears to have been about a 20 megabyte virus. It's got its own built-in SQLite database. Targets people. This is sophistication. But you know, mind you, these are governments, right? I mean, these guys have got the resources to build things like this. So seem to target people in the Middle East and then just collect all the information it can about what these guys are doing and send it back to these command and control servers, which kept cycling at a regular basis so people couldn't take them offline. Extremely sophisticated. It now seems the US and Israel were behind a lot of these as well, but I'm sure that all those other flags and a whole bunch of other ones are involved in the same sort of thing. These guys are going to pwn you. If they want to pwn you, these guys have got the resources. But I think for the most of us, unless you're in some sort of defence or military job, it's probably not going to be as big a thing to focus on in your work. So a little bit about why we're getting pwned, and obviously, based on this slide, there is a degree of it which is us as developers, we're building pwnable software. So we are building flaws into software. We're not the only reason websites are getting pwned. There's no doubt about that. We're not 100% to blame. But what's interesting is when we look at stats, and this is from White Hat's security paper, which came out a couple of months ago, called Website Security 101, and they believe that 90% of websites are pwnable, and the other 10% are probably still pwnable, but not quite so easily. But the point is, they're saying 90% of websites are vulnerable to things like SQL injection, cross-site scripting. Okay, so that's a huge number. That's probably a good percentage of the websites us in here look after. So I wanted to start to talk about some of the things we've been doing wrong, and then I want to talk about some things that are changing and a few other things that we need to consider when we're building apps. And I want to start with an example here. And these examples are going to be specific examples, but we'll look at some things in the periphery that help explain security. So I want to talk about Elmar. Does anyone here use Elmar? Not the hunting wabbits, the ELMAH. Okay, lots of people. So Elmar is great, error logging modules and handlers. And what's so great about Elmar is that it's a configuration-only setup process to get error logging on your web app. So you can say, look, I would really like to be able to log unhandled exceptions that happen on my website automatically. So all you got to do is drop in this DLL. I'm going to register a handler, which is elmar.axt, and I'm going to allow remote access. Once you do that, it makes it very easy then to fire up your browser and go /elmar.axt, and you will get the information you see here. So the sort of information we have here will be anything from internal SQL exceptions to null argument exceptions to anything which would cause an exception on your website. You can also explicitly log to Elmar, so you can log events programmatically. So Elmar's got a great amount of information in it. When you drill down into an event on Elmar, you start to get a lot of details like a stack trace. So everyone knows a stack trace when you're running locally, yellow screen of death, lines of code, where events have occurred, lots of nice sort of internal implementation information about your application. If you go down a little bit in one of those stack traces, you will also get things like server variables and you'll get request headers. So looking at this particular Elmar error here, we can see things like the .aspx auth cookie. Does anyone know what the ASPX auth cookie is? Some people half do. Okay, so ASPX auth cookie. When you set up forms authentication in an ASP.NET web application, The ASPX auth cookie is what is set to persist your session across requests. So HTTP is a stateless protocol. Every request is really just a brand new request on a different connection. The cookie is the thing which says, hey, this guy is already authenticated. When they make the request, this is who he is and this is the rights that he has. If you have that cookie, you can recreate the session. So if I can grab somebody's cookie and I can paste it into my own browser using something like edit this cookie for Chrome, I can hijack that session. So if I can find one of these Elmar logs and get an ASPX auth cookie, and it's still valid because they expire after a period of time depending on your settings, I can take over the session. Now this is why we try and protect these cookies so much. So this is why you hear people saying if you have an authenticated website, make sure every request is over HTTPS. Because if it's not over HTTPS, this information travels across the wire in the clear and you can then go and recreate the session. So if I get that, it's pwned. Now the thing is, there's a lot of Elmar pages out there which are publicly accessible. So if you go and do a Googledork, so a search which reveals an inept or stupid person, I think is the strict definition, and you search for elmar.axt in the URL, and you search for the string ASPX auth, there are 28,500 results out there. You can go to any one of those websites, get the ASPX auth cookie, put it in your browser, and if it's still valid, that's the pwning. If it's not still valid, you can always socially engineer someone to cause another error. So send them, for example, send them to an ASP.NET web app, a web forms app, and put a question mark script after the end. So a script will cause request validation, it will cause an error, it will generate another Elmar log, you go in there, you get the ASPX auth cookie, you copy it into here, pwned. Now, it gets worse than that too, because that was just for ASPX auth. There are 364,000 results for the elmar.axt handler, and then looking for the string error login, which is just that sort of welcome page. So there are just a huge number of Elmar pages out there. And I think everyone who put their hand up when I said who uses Elmar is now wondering, is my Elmar page visible? That's one of the things the SaferWeb tests for, little plug. So you can also look for things like, let's say, let's do a search for elmar.axt and let's look for SQL exceptions, okay? So when we do that, we'll start to find results like this. These are real ones too. I just went and searched for them. They're all publicly accessible. So we now start to find incidents where the internal implementation of the code has been disclosed. When we have internal implementation, we can start working towards SQL injection attacks or things like that. Other sorts of Elmar searches that are interesting, search for passwords, search for connection strings. It will scare the crap out of you, honestly, when you see the amount of information that is publicly accessible for people's websites. So here's the problem with Elmar. So this is the way Elmar is meant to be set up. And this is the guidance that Elmar had on their securing error log pages for quite a number of years. They don't have it on there anymore. But what was happening here is what that configuration will do is it will secure elmar.axt in the root. It won't secure elmar.axt in the admin, and it won't secure it in foo, and it won't secure it in handlers work in any path. Because the problem is handlers do work in any path. So you can take that elmar.axt and you can whack anything you want before that handler and it will work. Now the problem of course is that our location configuration is only securing elmar.axt in the root of the app. So this was not real good on their behalf. If you followed Elmar's security guidance, your website is publicly exposing Elmar, even if you think it is secure and you have checked it on /elmar.axt as an unauthenticated user. It's possibly still public. So the fix, and this looks a little bit verbose, but it's actually not too bad because it's just putting a bunch of stuff under this location tag. So what we want to do is we want to move the declaration of that handler and the authorization in under the location path. So this is the guidance that is now on the Elmar website. So if you have Elmar, go and do this. Maybe check it first, see if it's public, because then you probably want to ask some other questions like who's been looking at my Elmar log? Not just me, I guarantee you. All right, so that was Elmar. So moving on to trust. And a lot of security does sort of come down to trust. So we trust that a certain source is not going to do bad things to us. We don't suspect that a certain source might be malicious. So let's talk about untrusted data. So we often have this concept in security of untrusted data. And untrusted data is pretty much data that comes from any source that we don't control or we don't have absolute confidence in the integrity. So untrusted data, query strings, form variables, untrusted data could be in your database if other people have been able to put it in there. Untrusted data can also be in places like response headers. So if we take an example here, let's imagine we have written a little app and that app makes HTTP requests to a website, and when the response comes back, it saves the headers. Now this is what I do in the SaferWeb website because I want to know what software the server's running. So this would be a typical way of saving that. Okay? Into my server types table, I want to save the response header with the value server. Now this is interesting, this is true, you can go and look at this. If you make a GET request to Reddit, Reddit will give you a response that looks like this. Now the interesting bit is that bit. So this is real, you go to reddit.com now and look at it and all right, somebody there is having a bit of fun, no doubt. But this is why untrusted data applies to everything, everything. Now, for people who don't quite understand the implications of SQL injection, if we bring that other query back and we look at what would happen here, what this would do is we would terminate the statement, we would then drop the table server types. Now obviously Reddit is a pretty sort of low-tech attack. It expects you to have a server types table. And then it would terminate that statement, it would comment out everything else. So this would actually execute just perfectly. You wouldn't have a problem running this that you knew of, except that your table would be gone, which is a problem. So that's what Reddit does. Now the way we need to protect against untrusted data and protect against SQL injection is we've got to parameterize SQL statements. If you really, really wanted to use inline SQL, please don't use inline SQL, but if you really, really wanted to, you can parameterize it. When we add it as a parameter, that server value will stay as data and it won't break out of a data context and into a query context. Try not to do this. Try to use an ORM, Entity Framework linked to SQL, then Hibernate. Try and use stored procedures if you have to. Try not to do inline SQL. So, on to trust again. So, everyone saw what happened with GitHub a little while ago. GitHub had a little bit of a problem where a guy was able to demonstrate that he was able to commit code directly into the Ruby on Rails repository, which he was not meant to be able to do. Now, what this was what we call a mass assignment vulnerability. And I've called it the sort of shotgun update pattern because what happens with mass assignment is you have an entity somewhere in your system. That entity has a bunch of attributes. And what's happening is the application is saying all of the attributes that get sent to me, I'm just going to put on my entity. Send me whatever you like, just blast it to me. I'm going to put it on my entity and I'm going to save it. Now the good news is we don't have this problem in .NET. Well, we didn't, but now we do because now we've got MVC and we've got models that are passed to controllers and we've got a mass assignment risk. So I want to show you what mass assignment looks like in MVC. So let's take an example here. So this is a typical class that we would have in the database. This has been persisted via Entity Framework into our application tier. First name, last name, username, email, salary and comments. Fairly sort of typical entity. We also have a very typical user interface. And this is a self-service portal. So in this self-service portal, I need to be able to go through, change my name, change my email address. I cannot change my salary. I cannot change my comments. All of that information is read-only. Troy should not be allowed anywhere near this. It needs to be secure. Now, what's happening behind the scenes is we're using try-update model. So when MVC receives the post request and that controller action is executed, it receives my employee object, it is going to pull my employee from the database, it is going to run try-update model, and it is going to try and take the attributes from the employee, which has been passed into the controller action, save it on the database, get back out of there. Beautiful, this is so clean and neat and there's barely any crap in there, it's just easy, 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 easy. Now here's the problem with this. So this is a post request to that site. Now this has been captured via Fiddler. So I don't know if anyone uses Fiddler, but Fiddler is an HTTP proxy tool. It's a little free app. It's in, I think, getfiddler.com. If you run this locally, every request, every HTTP request your machine makes gets routed through Fiddler. so you can watch what the request is, the headers, the body, what the response is, also headers and body. Fiddler also lets you do things like use it as a proxy for your iPhone. So if you want to see what your iPhone, or if anyone's got Windows Mobile 7, anything like that, if you route it through Fiddler, you can see all of those requests, all that HTTP traffic that is going through there. So what this is showing us is we get a whole bunch of request headers, and we've also got a request body. And what the request body is showing us is that my first name, my last name, and my email address have been submitted when I posted that form. Now this is fine. So this is not doing anything stupid like posting my salary in a hidden form value or anything like that. This, on the surface, looks just great. Now here's the problem. So what we're going to do is we're going to use Fiddler to reissue this request. So Fiddler has got a composer tool, and what you can do is you can drag a request into Composer, and then you can just start manipulating bits. And what I've done is I have manipulated the bottom. I'm worth $1 million, damn it, and I want to change my comments, and that's what I want to save into my system. Now when I do that, I have just pwned our own payroll system. So how have I done this? So I've managed to submit information which is not meant to be submitted. Nowhere in the system did you see any reference to how we save money, how we save comments. It wasn't posted in any form data, but I've been able to exploit this. So the problem is try update model is very generous. So try update will basically take any attributes that belong to that model that are passed in the post request, it will assign them, and then if we then put that onto the data layer, it will persist that. So there are 5 things we can do. And the first thing is, let's be a bit explicit about what the controller is going to bind. So here we're explicitly saying, look, we can bind the first name, the last name, and the email, but that's all. So this is a whitelist of what we will allow to be bound by this controller. It's very, very explicit. We can do it the other way around too. So we can say, okay, great, let's save this, but I am going to say that I do not want to save salary and I do not want to save comments. So this then becomes a very implicit way of saving data. So what this is saying is, I don't know what other data you want to save, all I know is what you're not allowed to save. So this we would consider a blacklist. There's a really key difference in a lot of security discussions about whitelists and blacklists. Wherever possible, we want to try and whitelist, because a whitelist is saying these are our known good values, these are our known safe values. A blacklist says today we know that we don't trust these. If we go and add another attribute later on, and maybe it's an isAdmin flag or something like that, this will break. Well, it won't break, but it won't stop that isAdmin flag from being submitted. So we want to be careful about blacklists. So the other thing we can do is when we do try and execute try update model, during that method signature, we can explain which attributes we want to include in the update. So we've just got a string array here. Give me first name, last name, email. So again, this is like a whitelist or an explicit definition of what we want to allow. And we can also do the same thing in reverse, just like we did on the binding. So we can say, okay, I want to exclude salary and comments, and there's a slightly different method signature on try update model. Now ideally, and it's not quite so relevant to this demo, but we really want to be using view models. So we don't really necessarily want to take our data model and expose it to the UI. There's often not a one-to-one correlation. Either it's got additional data or it's got things that we just don't want to save. It's a little bit harder when you want to have some data that's read-only, but certainly if it was something like an isAdmin flag, we'd have a view model and it would not have isAdmin when it's returned to that view. It might have isAdmin on a different view model, which you might return to an administrator. So this is our mass assignment vulnerability in MVC. If anyone has any questions while I'm going through, please yell out because I'm ripping through this quite quickly. So the other thing that I thought we might talk about is what is changing in security. So security, excuse me, tends to be a pretty quickly evolving landscape. And I thought we might start with porn. Not pwn, porn. So we have long considered porn sites to be a risky area in terms of porn sites have got viruses, and if you go there, your computer will get infected and you'll get malware, and you'll get all of these sort of things. And these are the long-held beliefs. Now what's interesting is on the Ponometer, porn is actually going down to the bottom. So Semantic did a study recently. What Semantic found was that it is getting safer and safer to browse porn. Now, does anybody know what is getting more and more dangerous to browse? Any guesses? Ooh, sensitive.
Religious sites.
Yes, sir, religious sites. So what Semantic found was that there are more and more religious sites being infected with malware. And in fact, they found that you are 3 times more likely to get infected by malware if you go to a religious site or an ideological site than you are if you go to a porn site. This is not necessarily to try and influence your browsing habits. That's up to you. But it is an interesting observation about how things that we once held to be very risky are changing in profile, things that we once held to be very secure are changing in profile. There's probably a theory about why this is. I suspect that the theory may be that people visiting religious sites may be more trusting. People visiting porn sites may be naturally more suspicious. So, you know, in 3 years' time, it might flip on its head again. I don't know. Okay, so the one I want to talk about next, and this one gets a little bit interesting. So this is around password hashing, okay, about how we store passwords in our databases. So everyone saw the news about LinkedIn. LinkedIn, 6.5 million SHA-1 hashes of passwords were exposed, and this was a big deal. Unsalted, yes. Thank you, sir. That's the next slide. We're going to get to that. But no, you're right. It's unsalted. So let's talk about what that hashing means, what that salting means, and why that was a problem. So here's how we think we should store passwords. So we think we should hash our passwords. We used to think we should hash our passwords. So I want to talk about hashing for a moment. So what hashing is, despite the image, what hashing is it is a one-way deterministic process of taking an input string and creating an output cipher. Now it's one way, so it's not reversible. Hashing is not encryption. There is no key, there is no ability to take the ciphertext and convert it back to plain text. All you can do is rehash. So the traditional thinking was, okay, what we're going to do is when someone creates an account, we're going to take their password, we're going to create a hash, and we're going to store that in the database. Because then if anybody gets into the database, all they've got is this hash and they can't convert it back to plain text because it's a one-way process. Now, when someone logs in, you do the same thing. So someone logs in, they give you the plain text string, you hash it, and then you compare it to the hash in the database. So you're not comparing passwords, you're comparing hashes. So here is the problem with this. Now, the problem with this is not rainbows alone, but rainbow tables. Now, rainbow tables. So what rainbow tables do is they implement this ability to hash a vast array of strings. And they do that in a very sort of laborious way, and they create massive, massive files, and they then provide a mechanism to go through and very rapidly compare those files to the hashes in the databases. So I'll give you an example. A rainbow table might have, you might get a rainbow table that is SHA-1 hashing algorithm for every lowercase string from 6 to 9 characters. And the thing would be 100 gigabytes or something huge like that, because there's just trillions and trillions of possibilities. So that would be a rainbow table. You would then take a piece of software like Rainbow Crack, it's freeware software, and you would use Rainbow Crack to feed in your rainbow table and to feed in your hashes, and it would go through the rainbow table, it would look at every one of the hashes, it would compare it to the database, and when it matched, the rainbow table also knows the plain text equivalent of the hash, therefore it discloses what the password was. So rainbow tables work because hashing is such a predictable process. They've pre-computed all these hashes because they're using the same algorithms that you do when you store your password just with a hash. Now there's another interesting thing here as well, and I'll show you this on LinkedIn in a moment, but Google is awesome at cracking hashes. I mean, it is really, really good. And the reason Google is so awesome at cracking hashes is that if we take something from LinkedIn, so again, 6.5 million hashes, SHA-1 hashes from LinkedIn, and we take, say, this guy just here, and we plug him into Google, we'll get a bunch of results for that hash. When we drill down on it, you'll find something like this. Now, hang on, what did Google do in that? So Google cracked our hash in, what, about 0.19 seconds. Okay, so I told you it was awesome. Now the reason this works is because there are a heap of sites out there that have plain text and hashes. So people have gotten breaches like LinkedIn, and these guys are making a sport of it. They're going through cracking hashes, regenerating passwords, hashing them, and then saying, you know, what matches up. So there are gazillions of examples like this on the web. And again, because the hash is deterministic, because we can hash the same password anywhere and get the same result using the same algorithm, that's why this works. Okay, so here's how we think we now need to store our passwords. And the variable here is the salt. So the idea of a salt is a salt gives us random bytes. So the problem we had before was if we take a password and we hash it, we always get the same result. And that's why rainbow tables work, that's why the Google cracking works. A salt is just a set of random bytes. If we add random bytes to the password and then we hash it, we're always going to get a different result. So the same string will always give you a different hash. Now what happens in this model is in your data layer, you then store the hash, which is what you would have stored in the first example, but you also store the salt. And the way it works is that when someone logs in, you get their username and you say, okay, go to the database for that username, give me the hash and give me the salt, and then it adds the salt and the password together and it hashes it and then it compares it to the hash from the database. So it just repeats the hashing process. So think of it like this. When we were just hashing passwords, it's a little bit like a needle in a haystack. So say LinkedIn, 6.5 million little pieces of straw in the haystack. So it was a big haystack, but it was one haystack. When we salt, effectively what we do is every single account has its own little haystack because every single account has its own salt. Now the reason why this works well is because if somebody wanted to attack this, they have to go through and brute force every single one of those haystacks. So they'd have to take the first account, they'd have to get the salt, they'd have to get the hash, they'd have to get, say, a whole list of different possible passwords, add the salt, hash it, compare it, doesn't work, move on to the next one. Take a very long time, and then when they get to the end of it, they have to do the same thing for every other account that they've breached from the database. Now the problem with all of this is that that's a lot of work. Going through all those haystacks is a lot of work. But what if you could do it fast enough? So what if you could go through those haystacks at such a rate of knots that it wouldn't matter that you've got 6.5 million haystacks? You just go and parse them all very, very quickly. So the problem with hashing is one of speed. And we're going to talk about speed in just a moment. What I want to look at first is hashing passwords at a very fast rate. So what you see here is an AMD Radeon 7970. It's a fast graphics card. It's a consumer level graphics card though. It's about a $500 graphics card here in Australia. Now what this guy can do is it can compute over 4.7 billion hashes per second. Now GPUs are really, really efficient at creating hashes. There is something about their internal architecture that allows them to do this 4.8 billion times. A fast CPU is much, much slower. Apparently the GPU is something like 150 times faster to crack hashes. Now what this means is that if we can get this guy, we can start computing hashes very, very quickly. So 4.7 billion is for MD5. MD5 is a hashing algorithm which is pretty antiquated. Most people consider it unsuitable anymore. If we go to SHA-1, like in LinkedIn, we get down to about only 2.2 billion per second. If you go to SHA-256, it's about 1.1. So it's a ridiculously fast rate. All of that is using this little guy down here, which is hashcat. Hashcat.net has a free piece of software. It doesn't have to have an AMD Radeon 7970. You can run it against a CPU, you can run it against other GPUs. But that is the software that allows you to generate these hashes at an extremely fast rate. Okay, so let's consider this in terms of numbers. So the first thing is we really suck at choosing passwords. We as society, I mean, all of us here are good. Everyone else really sucks at choosing passwords. Last year I did some analysis on one of the Sony breaches. So everyone knows that Sony got breached gazillion times last year. They had problems everywhere. And one of their breaches was for Sony Pictures. Now Sony Pictures didn't do any of this. They didn't use salt, they didn't hash, they just had plain text. So as bad as that was, it gave us a really nice little ecosystem to look at how people create passwords. And what I found when I went through this is that 82% of passwords were 9 or less alphanumeric characters. Lowercase. I did say lower. I mean, that's crazy. But that's the way people create passwords. Now, if we assume that the password had to be at least 6 characters, we get 104 trillion different possible passwords that could fit into that 9 or less lower alphanumeric characters between sort of 6 and 9. So that's a very large number. But if we throw that number at that fast GPU, it's only 6 hours. Okay? So for one account, because you've got to remember, it's 6 hours to go through every single possibility within that character space, but you're going to have to do that for every single account. So 6 hours seems pretty fast in order to have an 82% chance of breaking that password. So that's a salted hash. Now the thing is though, it's a little bit slow. And it's slow insofar as it's not as fast as it could be, because the reality of it is that when people create passwords, they don't create random 6 to 9 character lowercase and it's just totally random. They adhere to patterns. They adhere to things like password 1, password with an @ symbol, pass underscore word. So they do these stupid sort of things. And look, I mean, I've done it, okay? Everyone's probably done it. You get into a pattern, I don't want to remember another bloody password, so you take shortcuts. But the problem is it does make them very predictable. So what happens is you end up with password dictionaries. There are lots of different password dictionaries online, and a password dictionary is not like a Webster or an Oxford or something like that. A password dictionary is made up of the sort of words that we use as passwords. So when you look at the words here, you're not going to find them, most of them, in a normal dictionary. Now what happens with these password dictionaries is they can be huge. So in the example I'm going to show you, I've used a password dictionary. It's got 23 million words in it. I think it was about a couple of 100 megabytes text file. There are lots of password dictionaries out there, very frequently based on other breaches. And they're based on other breaches because we know people reuse passwords. So if we can go to something like that Sony breach, get all of those passwords and put that in our dictionary, there's a very high correlation between the people that have those passwords using the same thing on their Facebook or their Twitter or somewhere like that. So we're building up a picture of the way people choose passwords. To give you an illustration of how random and how large these password dictionaries are, there are over 5,000 occurrences of the word boob in that password dictionary. Now I'm just trying to give you a sense of how random and variable these dictionaries are. Let me skip past that. Now, all right, so let's get on to the cracking bit. So, ASP.NET membership provider. Does anyone here use ASP.NET membership provider? Yes? It's mostly very good. It's a little bit that's not very good that we'll get to in a moment. So what the membership provider allows you to do is when you start a new ASP.NET Web Forms or MVC app, most of you have probably seen that template already has a register link, already has a login link. It's very easy to generate the schema of a database behind that, which is what we're looking at. And that schema tracks everything from the person's name to the person's email address, all the way through to the password salt and the password itself. So what you're seeing here is just over 39,000 rows in my membership database. So what I've done is I've gone and taken all of those Sony passwords, I've pumped it into the membership provider, and I've generated salted hashes. So if you use the membership provider, you have a database that looks like this, if you're using the default configuration. So remember, this is what we consider secure, because every one of those passwords is a salted hash. Now here's where it got really interesting. So I've taken that list of secure passwords, and I've taken my 23 million word dictionary, and I've plugged it into hashcat. And what hashcat does is, first of all, it gives us the salt. Okay, so it's gone through, however many tens of thousands of rows I had. Here's the salt, here's the password, here's the plain text. So hashcat has actually gone and cracked every single one, not every single one, about 63%, of our SHA-1 salted passwords. It's done it all in 44 minutes and 56 seconds. And that's almost 25,000 passwords. So that's your salted SHA. It's pretty much worthless, which is a real problem. Now the other things that you'll see here, just out of interest, it's done it with 258 million passwords a second. Now, as we know, 258 million is actually really slow because we wanted to get something like 2.2 billion. And the problem is that you just can't feed data into the GPU fast enough. So hashcat's gone through this great big password dictionary and it's fed each word into the GPU and then it's hashed it using the salt of each one of the passwords in the membership and compared it to the hash. And there's a little bit of a bottleneck in terms of pushing stuff in. So we only get 250 million attempts per second. But this is, I think, probably one of the most important lessons to leave you with today. Salted SHA-1. Okay, so the problem that we have here is that we need to make everything go slow. And this is a very counterintuitive concept for us as developers because we want to make everything go as fast as we possibly can. We want to shave milliseconds off everywhere. And I'm standing up here going, no, go the other way, make it slower. But we're only talking about when a hash is created. So that's at registration, that's at logon, and that is at password change. So this is not like every hit to the web page has got to be slow. This is those key events we want to slow down. Now, if we use something like bcrypt, we can tailor what they call rounds. And what a round is it's an exponential increase of the workload that the hash needs in order to create the output. So 4 rounds might take 50 milliseconds. 5 rounds takes 100 milliseconds. 6 rounds takes 200 milliseconds. You can tailor it. You've got to set it at the start because you can't go and change it halfway through, otherwise when someone logs in there's a different number of rounds. But you can run this up on your hardware and say, how do I want this to work? So that's sort of the turtle of hashing algorithms. The other thing we can use is we can use the snail of hashing algorithms. Password-based key derivation function. So what PBKDF, peanut butter keeps dogs friendly too, does is it defines a number of iterations. So you can still use SHA, you can still use MD5, but rather than just hashing it once, it's going to go through and hash it 1,000 times, 10,000 times, 100,000 times. The nice thing is you decide. So you decide how slow do I need this hash to run. Now, of course, the problem is that when it starts to run slower, you then have other problems as well. So if my password hashing function suddenly takes 10,000 times longer, am I going to be vulnerable to DOS? So can someone come along and start pounding that page and trying to log on, and every time they log on, we've got this lengthy duration which then has a higher probability of taking us offline. The other thing is what's it going to do to the performance of the overall box? Is my CPU going to be sitting there tied up just trying to generate hashes rather than being able to serve web pages and doing the things that we actually want it to do? So you need to find a sweet spot. On slow things, we've got the Toyota Prius, which is the script. So we have other hashing algorithms like script, which do a similar sort of thing. Some of these combine a combination of using a slow algorithm as well as using a very high number of iterations. So the big thing to take away is don't use the ASP.NET membership provider out of the box and expect that SHA-1 is going to be secure. There are NuGet packages for things like bcrypt. Those are on my blog. I posted a blog last week on troyhunt.com which talks about some of those other packages. There are also some things that appear to be changing in the membership provider with .NET 4.5 that I've got to understand a little bit more about. But there are things that are coming down the line that make this easier, but just be really, really cautious about the stuff you've got there already. Now, the final thing on hashing as well is that all of this, sometimes people say, well, look, you know, if you had secured your damn website in the first place, this wouldn't be an issue. So none of this is about saying, hey, now you don't need to worry about website security because if they get our passwords, they're all hashed. This is sort of your last line of defense. So you've still got to do all of the good stuff that's in OWASP Top 10 and all of the sort of normal common web practices for securing data. And then this is kind of like, okay, everything has gone really, really bad. How do we then protect it? So for example, if LinkedIn had done this, it would have been a different story. So out of those 6.5 million, maybe they would have cracked some of them, but they wouldn't have cracked the percentage that they had. So where I want to wrap up, because some of this has sort of been a little bit depressing. Everyone's getting pwned, your Elmar's visible, everyone now knows their hashing stuffed as well. I wanted to end on a little bit of a happy note for us, which is the pwners getting pwned. So these guys are getting caught. So this handsome devil here, Hector, he's the guy who founded lulzsec, and it didn't end up working out real well for Hector because the FBI got him. So they got him, I think about September last year, and they turned him, so he became like the inside snitch. And apparently he was facing about 124 years of jail, which is a hell of a long time. Now when they turned him, he then started turning all the other guys. So we get guys like Ryan Cleary, 20 years old. Jake Davies, 19 years old. You can see a bit of a trend with these guys. This guy is a fair income geriatric in the scheme of the other players, 17 years old. All of these guys are now pleaded guilty to charges of DOS, and they've pleaded not guilty to charges of posting data on Pastebin. So we'll see how it all sort of finishes up. But I think what's interesting about this, a lot of these are just kids, you know, they're just in there mucking around. They probably don't understand the extent of what they're doing. But the one that I do find most funny, and this was in the news a little while ago. So this clearly is a geotagged photo. And what happened here, there's a group called Cabin Crew, who are in the, some of them at least are in the US, and they were going around hacking law enforcement, which is probably a little bit like poking the tiger. But they thought it would be funny to get this guy's girlfriend to take this photo of her breasts and a little inflammatory sign. Now, what they didn't realise is when she took this, she took it with her iPhone. And what does your iPhone do? Your iPhone geotags. Posted it up online, and the cops went, hey, look at this. There she is, down in Montana. So the cops went down there and quickly figured out that her boyfriend was Eugenio Ochoa in Texas, and now he's facing charges. So they're just so stupid. So I thought that was a funny sort of note to wrap up on. But I do want to leave you with some things to take away with you. So sort of 5 lessons. Number 1 is understanding that there are different motivations. You don't necessarily have to think of yourself as a target in order to be hacked. Some people are just opportunistic. They just want to get in there and have a go. And that's what's happening with a lot of these Anonymouses and lulzsecs of the world. I think also acknowledging that we have a very high percentage of websites which are vulnerable. You know, it's a bit of a hard pill to swallow, but 90% is very high, and it probably affects all of us, myself included here. So understand that OWASP Top 10. If you've not read it already, go and get that free ebook from troyhunt.com, and go to owasp.org as well. There's a lot of really good information on there. So watching out for shortcuts too. So things like Almar are awesome, try update model are awesome, but you've got to understand what's the security profile of that, what's the risk. Because something so simple as dropping Almar, and particularly when you go and get it from NuGet, you know, it's like add package, Almar, boom, done. And then your website's exposed. So be really careful with those shortcuts. Those changing security positions as well. So again, I'm not giving advice on whether you should browse porn or browse religion, but be conscious that the security landscape does change. And finally, you may get pwned, and if you're really going to get pwned and you're really going to antagonise people, please don't take photos of your breasts. Thank you.